Tonight, our journey takes us to a world that seems to stretch the very limits of imagination. A planet so vast, it compels a reconsideration of the fundamentals of how planets form. This is a world of such immense volume that our solar system's own giant, Jupiter, could fit comfortably inside, with significant room to spare. Yet, for all its colossal size, this sphere possesses a remarkably low density, so little that it would actually float if placed within a theoretical ocean large enough to contain it. We are familiar with large planets. Jupiter has been a subject of human study for centuries, the undisputed king of our own planetary family. But this faraway world makes Jupiter appear quite modest. If you were to imagine Jupiter as the size of a grapefruit, this planet would be a watermelon. It resides more than 1,000 light-years from Earth, orbiting a star largely unknown to the public, in a corner of the cosmos we are only now beginning to map. To appreciate the significance of this discovery, a brief look into our past is essential. For nearly all of human history, our knowledge of planets was confined to those within our own solar system. Mercury, Venus, Mars, Jupiter, and Saturn were the wandering stars that ancient observers noticed moving against the static backdrop of the constellations. Later, our celestial family grew to include Uranus, Neptune, and for a period, Pluto. But every one of these worlds orbits our own sun, and we had no definitive proof that other stars hosted planets. For generations, astronomers held the assumption that they most likely did. It seemed improbable that our sun would be unique in having a retinue of orbiting worlds. The universe felt too vast and filled with stars for our system to be such a profound exception. However, there is a great distance between assuming something exists and proving its existence. The challenge of finding planets around other stars is immense. To put it into perspective, the task is comparable to standing in Los Angeles and trying to detect the flicker of a firefly right next to a brilliant searchlight beam originating from New York. Stars are overwhelmingly bright, while planets are comparatively tiny and generate no light of their own. They merely reflect the light from their parent star, and this reflection is billions of times fainter than the star itself. Then, in 1992, the paradigm shifted. Astronomers made the first confirmed discovery of exoplanets. But these worlds were not orbiting a star like our Sunday. They were found circling a pulsar, the incredibly dense, rapidly spinning remnant of a star that had undergone a supernova explosion. While this was a monumental discovery, pulsars are extreme cosmic objects, so finding planets around one did little to answer the question of whether ordinary stars had planetary systems. The true turning point arrived in 1995, when astronomers Michel Mayor and Didier Queloz reported they had detected a planet orbiting a sun-like star known as 51 Pegasi. This new world was unlike anything in our own solar system. It was a gas giant with a mass similar to Jupiter, but it orbited its star at an astonishingly close distance. Its orbital period was just over 4 Earth days, placing it so near its star that its surface temperatures exceeded 1,000 degrees. This finding sent shockwaves through the astronomical community. No one had anticipated discovering a Jupiter-sized planet in such a tight orbit. Our own solar system's model suggested that gas giants like Jupiter and Saturn form in the cold, distant outer regions, where ice and gas could coalesce during the system's formation. Discovering a gas giant practically touching its star felt as incongruous as finding a polar bear perfectly adapted to life in the Sahara Desert. It simply should not have been possible. And yet, it was there. This world, and others like it found shortly after, came to be known as hot Jupiters. They were the first category of exoplanet to be discovered in significant numbers, not because they are the most prevalent type in the galaxy, but because our methods make them the easiest to find. A massive planet in a close orbit exerts a stronger gravitational tug on its star, creating a more pronounced wobble for us to observe. It also blocks a larger portion of the star's light when it passes in front, leaving a more obvious signature for our instruments to detect. This brings us to the technique used to find the largest planet ever documented. The discovery was made using a method known as the transit technique. The principle behind it is beautifully straightforward. When a planet crosses the line of sight between its star and an observer on Earth, it momentarily obstructs a small amount of the star's light. By carefully monitoring a star and measuring its brightness over time, you can observe a slight, temporary dip as the planet makes its passage. The star's light dims and then returns to its normal level once the planet has moved on. The depth of this dimming reveals the planet's size in relation to its star. A larger planet blocks more light. The interval between these dips tells you the planet's orbital period. This is the work of the HAT project. The name is an acronym for Hungarian-made automated telescope, a system of small, robotic instruments whose sole purpose is to hunt for these transiting exoplanets. The project began in 2003 with a single instrument in Arizona and has since grown into a global network with telescopes in Hawaii, Arizona, Namibia, Chile, and Australia. This worldwide distribution enables astronomers to maintain nearly continuous observation of target stars, ensuring they can catch transits regardless of the time of day or night. The telescopes themselves are not especially large. Each has a lens about 4 inches in diameter, similar to a high-end amateur telescope. Their strength lies not in size, but in their automation and relentless dedication. Night after night, these instruments monitor hundreds of thousands of stars, measuring their brightness with incredible precision, searching for those characteristic dips that signal a potential planet. Over a period from 2005 to 2008, the HAT network gathered data on a star located in the constellation Hercules, approximately 1,044 light-years away from Earth. The telescopes registered a periodic dimming of this star every 481 Earth days. Its brightness decreased by about 2.5%. This was a substantial dip. To put it in perspective, if Jupiter were to transit our Sun as viewed from a distant star system, it would block only about 1% of the light. Something was crossing in front of this distant star, and that something was enormous. After several years of follow-up observations to eliminate other possibilities and verify the finding, the planet's existence was officially announced in 2017. As the team of astronomers scrutinized the data, they began to understand that they had uncovered something truly exceptional. Let us now examine the key characteristics of this world, stated with clarity and precision, before we delve into their profound implications. This world's diameter measures approximately 2.1 times that of Jupiter. Given that Jupiter spans about 88,000 miles at its equator, this distant planet extends to nearly 185,000 miles across. One could imagine placing about 23 Earths side by side to match its width. In terms of sheer volume, this single world could contain roughly 12,000 planets the size of our own. It holds the distinction of being the largest confirmed exoplanet discovered by its radius. Yet, this is where the picture becomes truly peculiar. Despite its colossal size, this giant possesses only about 0.45 times Jupiter's mass, based on the most recent findings published in 2025. It's an intriguing contradiction. A planet more than twice Jupiter's size that weighs less than half as much. This disparity means its density is remarkably low, calculated at just 0.06 grams per cubic centimeter. To put that in perspective, water has a density of 1 gram per cubic centimeter. This world is so diffuse that it would float in water, much like a child's toy in a pool. The planet orbits an F-type star, a class of star hotter and more brilliant than our own Sunday. Its host star contains about 1.6 times the mass of our Sun and has a diameter roughly 1.85 times larger. The planet itself follows an incredibly tight path, circling its star at a distance of only about 7 million miles. It completes a full orbit in a mere 4.81 Earth days, a testament to the tremendous speed at which it travels. At such close range, The planet's equilibrium temperature is estimated to be around 1,900 Kelvin. Kelvin is the temperature scale preferred by scientists, where 0 represents absolute zero, the coldest temperature theoretically possible. A reading of 1,900 Kelvin is equivalent to about 2,960 degrees Fahrenheit, or approximately 1,620 degrees Celsius. This level of heat is sufficient to melt most metals, causing the planet to glow faintly with its own thermal energy. This is a world perpetually baked by the intense radiation of its parent star. The central question this discovery presents is how a planet can be so immense yet so insubstantial. Jupiter, our solar system's own giant, is composed primarily of hydrogen and helium, the two most lightweight elements in the cosmos. Hydrogen accounts for about 90% of Jupiter's total mass. Deep within Jupiter's interior, the pressures become so extreme that hydrogen begins to behave in unusual ways. Near the planet's core, hydrogen is compressed so intensely that it transforms into a metallic state, capable of conducting electricity like a metal despite being formed from the lightest of atoms. This distant giant is also thought to be made mostly of hydrogen and helium. The key difference, however, is that it is not squeezed into a dense sphere. Instead, its material is puffed up, like a marshmallow expanded by heat. The same amount of substance is spread across a much greater volume, which explains its astonishingly low density. The intense heating from its nearby star is considered the main driver of this inflation. The physics are straightforward. When a gas is heated, it expands. As energy is added, the molecules within the gas move more rapidly, spreading out to fill a larger space. On Earth, this principle allows hot air balloons to rise. The heated air inside becomes less dense than the cooler air outside, creating lift. If we scale this effect to a planetary level, we can see how the upper atmosphere, constantly absorbing radiation from its star, would heat up and expand. Over billions of years, this persistent heating has likely caused the planet to swell to its current dramatic size. However, simple heating models alone do not seem to fully account for the extreme puffiness observed. It seems something more must be at play. Scientists have put forward several other mechanisms that could be contributing. One idea centers on the planet's orbit. If its path is slightly elliptical instead of perfectly circular, the star's gravity would repeatedly squeeze and stretch the planet. This process, known as tidal flexing, generates internal heat through friction, much like bending a paperclip back and forth warms it up. Over eons, this tidal heating could inject a significant amount of energy deep into the planet's interior. Another possibility focuses on the planet's magnetic field. Gas giants often possess powerful magnetic fields, which can interact with the stellar wind, the continuous stream of charged particles flowing from the star. This interaction might generate electrical currents within the atmosphere, depositing energy far below the surface and heating the planet from the inside out. A third explanation posits that specific layers in the atmosphere could act as an insulator, trapping heat and preventing it from escaping into space efficiently. This would keep the interior hotter than otherwise expected, maintaining the planet's inflated state. The simple truth is that we do not yet have a complete answer for why this planet is so extraordinarily puffy. It remains one of the compelling open questions in exoplanet science, a puzzle that astronomers are actively trying to piece together. This world, as one of the most pronounced examples of an inflated planet, serves as an invaluable natural laboratory for investigating this phenomenon. At such a close distance to its star, the planet is almost certainly tidally locked. This means that one hemisphere perpetually faces the star, while the other is turned away, shrouded in the constant darkness of space. Our own moon is tidally locked to Earth in this same manner, which is why we only ever see one side of it. This arrangement creates a world of stark contrasts. The day side, the hemisphere bathed in starlight, is relentlessly bombarded by radiation, with temperatures soaring to thousands of degrees. The night side, conversely, receives no direct starlight and would be considerably cooler, although atmospheric circulation likely transports enough heat to prevent it from freezing completely. The boundary between these two realms, known as the terminator, would be a region of eternal twilight. Here, winds gusting from the scorching day side toward the cooler night side could reach incredible speeds, possibly thousands of miles per hour. The entire atmosphere is likely a violent, churning maelstrom, driven by the extreme temperature differential between the zones of perpetual day and perpetual night. When we consider the atmosphere of this world, it's important to understand it bears no resemblance to Earth's. There is no breathable air and no meaningful quantity of oxygen. The atmosphere is likely dominated by hydrogen and helium, the very same elements that constitute the bulk of the planet. But at temperatures approaching 3,000 degrees Fahrenheit, a truly exotic chemistry becomes possible. Many materials that we know on Earth as solids or liquids would exist here as gases. For instance, titanium oxide and vanadium oxide compounds used in paints and industrial applications might float as vapor in the atmosphere, absorbing starlight and further heating the upper layers. Some scientific models even suggest that the hottest gas giants could have atmospheres where elements like iron and magnesium exist as a vapor. It is a world where iron, a metal we know for its incredible hardness, exists as a vapor floating through the air. On the planet's searing day side, this atmospheric iron could condense in slightly cooler zones, forming droplets of liquid metal that fall through the sky like rain. The atmosphere might also contain clouds made of silicate. Here on Earth, silicates are the fundamental building blocks of rock, such as granite, sand, and glass. In the extreme temperatures of this alien world, however, silicate materials could vaporize and subsequently coalesce into clouds. The picture that emerges is one where clouds of fine rock dust drift through a hydrogen-rich atmosphere, pushed by winds that rage at supersonic speeds. The colors of this world would likely be entirely alien to our experience. Its appearance would depend on the specific chemicals present and how they interact with light. The planet could be profoundly dark, almost black, absorbing the vast majority of the starlight it receives. Alternatively, it might emit its own eerie light, glowing with strange hues from its superheated gases. Since we cannot take a direct photograph of the planet, our understanding is built upon scientific models and observations of other, similar worlds. Discovering this planet and measuring its basic characteristics was merely the first step. To truly comprehend this world, astronomers aim to study its atmosphere directly. What is truly remarkable is that we possess the technology to do precisely that. When the planet passes in front of its host star, a portion of the starlight filters through its atmosphere before continuing its journey to our telescopes. Different gases within that atmosphere absorb light at very specific wavelengths. By meticulously analyzing the star's light spectrum during one of these transits, researchers can determine which wavelengths have been absorbed, thereby identifying the gases present. This method, known as transmission spectroscopy, has successfully detected water vapor, sodium, potassium, and other elements in the atmospheres of distant exoplanets. This particular giant world, with its enormous size and exceptionally puffy atmosphere, presents an ideal subject for transmission spectroscopy. A more expansive atmosphere allows more starlight to pass through it, resulting in stronger and more easily detectable spectral signatures. The James Webb Space Telescope, which began its mission in 2021, has the power to analyze this planet's atmosphere in a level of detail never before possible. The knowledge we gain from this world will deepen our understanding of the entire category of inflated hot Jupiters. These planets represent some of the most extreme environments in the cosmos, existing at the very edge of what is allowed by the laws of planetary physics. By examining them, we learn not only about these specific worlds, but also about the universal processes that form and shape all planets. To fully appreciate what makes this discovery so special, it is helpful to place it in context with planets we know better. Jupiter is the undisputed giant of our own solar system. As the largest planet orbiting our Sun, its mass surpasses that of all the other planets in our system combined. If Jupiter were a hollow sphere, you could place approximately 1,300 planets the size of Earth inside it. Jupiter is accompanied by at least 95 known moons and is famous for its Great Red Spot, a storm larger than our entire planet that has been churning for centuries. Jupiter is undeniably magnificent, yet this distant world is more than double Jupiter's diameter. By volume, you could fit roughly 9 Jupiters inside of it. The difference in scale is simply immense. For further comparison, consider some other giant exoplanets. WASP-79b is another inflated hot Jupiter, orbiting a star some 790 light-years from us. Its diameter is about 2 Jupiter radii, making it vast but still smaller than the planet in question. Another world, WASP-17b, discovered in 2009, was for a time thought to be the largest known exoplanet, with a diameter approximately 1.89 times that of Jupiter. Even this was smaller. Then there is Kelt 9b, one of the hottest exoplanets ever found, with a dayside temperature that exceeds 7,800 degrees F, a temperature hotter than some stars. Kelt 9b measures about 1.89 times Jupiter's diameter, intensely hot and extreme, but still not as large as the world we are considering. There have been other candidates that appeared to be larger, but upon more detailed investigation, many of these have been reclassified as brown dwarfs. Brown dwarfs are a class of celestial objects that occupy a middle ground between planets and stars. They are not massive enough to sustain the hydrogen fusion that powers a true star, but they are significantly more massive than planets, typically having at least 13 times the mass of Jupiter. Some brown dwarfs can be quite large and puffy, but they are fundamentally not planets. This record-breaking world, with a mass estimated at roughly 0.45 Jupiter masses, is unequivocally a planet. It lacks anywhere near the mass required to be a brown dwarf. It is, quite simply, a planet that has been swollen to an incredible size by the intense radiation from its parent star. This may lead one to wonder how large a planet can possibly become. A fascinating principle of physics dictates that there are indeed limits. As a gas giant accumulates more mass, a counterintuitive effect occurs. Adding more material does not always make the planet physically larger. Instead, the increased gravitational force compresses all the existing gas, causing the planet to become denser. Jupiter itself is actually close to the maximum size a gas giant can attain simply by adding more mass. If you were to add more hydrogen and helium to Jupiter, it would scarcely increase in size. It would primarily become more dense. The planets that manage to exceed Jupiter's diameter do so not because they are more massive, but because an external force is puffing them up. If you could remove the intense heat from this distant giant and allow it to cool over billions of years, it would contract, shrinking to a size similar to, or perhaps even smaller than, Jupiter. This is precisely why inflated hot Jupiters are such compelling subjects of study. They demonstrate how external conditions can radically reshape a planet's fundamental structure, showing that the same quantity of matter can exist in vastly different forms depending on the circumstances. It is highly probable that this giant planet did not form in the location where we observe it today. At a distance of only 7 million miles from its star, the early protoplanetary disk would have been far too hot for the ices necessary for giant planet formation to condense. There simply would not have been enough solid material to rapidly build a massive core. And yet, there it is, a gas giant in an orbit that should have been impossible for it to form in. The prevailing explanation for this is that the world came into being much farther away from its star, in the cold outer regions where gas giant formation is common, and subsequently migrated inward. This migration likely occurred due to interactions with the protoplanetary disk itself. As the young planet moved through the disk, its gravity would have created spiral density waves, regions where the gas was slightly denser or less dense than average. These waves would have exerted a gravitational pull on the planet, effectively draining angular momentum from its orbit. Losing this momentum caused it to fall closer and closer to its star. Over a period of millions of years, the planet spiraled from the outer solar system into its current, blisteringly hot orbit. This mechanism, known as Type II migration, is now believed to be a common process in the early lives of planetary systems. Many hot Jupiters likely reached their current positions through this migratory process, though the details of the journey vary from one system to another. Some planets appear to move quickly, settling into orbits extremely close to their stars. Others take a more gradual path or halt their inward spiral partway through. Depending on specific conditions in the disk, a world might even be pushed outward rather than inward. There is also the possibility of influence from other planets in the system. Gravitational nudges from companions we have not yet detected could have reshaped this planet's trajectory over cosmic time. These interactions might have elongated its orbit, amplifying tidal heating, or they could have been the very force that guided it to its current position. The system is still being studied. Future observations could very well uncover these hidden worlds. Astronomers might also spot tiny irregularities in the giant's orbit. These would be subtle hints of gravitational pulls from unseen neighbors, suggesting the system is more complex than we currently realize. It raises one of the most compelling questions about hot Jupiters like this one. How long can they survive? These planets exist in a precarious state. They orbit so near their parent stars that they endure extreme environments. Some hot Jupiters are known to be slowly shedding their atmospheres. Intense stellar radiation strips away their outer layers, causing gas to stream off into space. Over billions of years, this process could significantly diminish a planet's mass. It could potentially transform a gas giant into a bare rocky core or even destroy it entirely. The exceptionally low density of this particular world might make it especially vulnerable to atmospheric loss. Its gravity is relatively weak for a gas giant because its mass is spread across such a large volume. The escape velocity, the speed gas molecules need to reach to break free from its gravity, is lower than for a denser world. This means it is easier for its atmospheric gas to be stripped away. However, this world is situated at a greater distance from its star compared to some ultra-hot Jupiters. There are planets that complete an orbit in less than a day, experiencing even more ferocious radiation. Some of these ultra-short period planets are actively evaporating, with observations showing vast tails of gas trailing behind them as they orbit. This planet, with its nearly 5-day orbit, is not in immediate danger of being boiled away. The nature of the host star is also a critical element. F-type stars are more luminous than our Sun but have shorter lifespans, as they consume their hydrogen fuel more quickly. This star is estimated to be about 3 billion years old. It probably has several more billion years of stable life ahead of it, but eventually, it will exhaust the hydrogen in its core. It will then begin evolving into a red giant. As it swells, it will engulf any planets in close orbits. This enormous world, for all its size, will be consumed by its own star. This is the eventual fate for a great many planetary systems. Our own solar system will experience a similar event in about 5 billion years. Our Sun will begin its transformation, consuming Mercury, Venus, and possibly Earth. Every planetary system has an expiration date, one set by the lifespan of its star. This giant world exists now. It exists in this particular moment of cosmic history. A billion years from now, it might look very different. 2 billion years from now, it might not exist at all. We are fortunate to be able to observe and study it during this window of time. The distance to this remote world is almost impossible to truly grasp. The planet is about 1,044 light-years away. A light-year is the distance that light travels in 1 year. Light is the fastest thing in the universe. It moves at about 186,000 meters per second. That means light can travel around Earth about 7.5 times in a single second, and it can cross the distance to the Moon in about 1.3 seconds. But even at this incredible speed, light takes time to cross the vast distances between stars. Light from our star reaches us in about 8 minutes and 20 seconds. Light from Proxima Centauri, the nearest star beyond our solar system, takes about 4.25 years to reach us. The light from this distant world takes over 1,000 years. When we look at this star, we are seeing it as it was a millennium ago. The light entering our telescopes has been traveling through space since around the year 1000. At that time, the Norman conquest had not happened, the first universities in Europe would not be founded for another century, and the Crusades had not begun. That is how long that light has been traveling to reach us. This means we are always looking into the past when we observe distant objects. For this distant planet specifically, the observations we make today show us the planet as it was over 1,000 years ago. If something dramatic happened to that planet yesterday, we would not know for another 1,000 years. The light carrying that information has not reached us yet. The distances between stars also create total isolation. Even if we could travel at the speed of light, which physics tells us is impossible for objects with mass, reaching this world would take over 1,000 years. With any technology we can currently imagine, the journey would take much longer. Voyager 1, the fastest spacecraft we have ever sent out of the solar system, travels at about 17 meters per second. At that speed, reaching this star would take over 11 million years. These distances mean that detailed exploration of this planet is beyond our reach. With current technology, we cannot send a spacecraft to visit. We cannot collect samples. We cannot take close-up photographs. Everything we know about this distant world has been learned by carefully analyzing the tiny amount of light that reaches us across 1,000 light-years of space. And yet, despite these incredible distances, we know quite a lot. We know the planet's size, its mass, and how long its year is. We know the temperature of its atmosphere. We are beginning to understand its chemical composition. This shows the ingenuity of astronomers and the power of modern technology. From faint starlight, we can deduce the properties of a world so far away that no human will ever visit it. You might wonder why astronomers are confident about these measurements. After all, we are talking about a planet over 1,000 light-years away. How can we know its size, its mass, and its temperature with any confidence? The certainty behind these claims rests upon the rigorous foundations of modern astronomy, where independent techniques consistently yield the same conclusions. The planet's dimensions, for instance, were revealed through the transit method, which operates on straightforward geometric principles. As this world journeys in front of its star, it obstructs a specific fraction of the star's light. The degree of this dimming corresponds directly to the ratio between the planet's area and the star's area. This is a calculation of pure geometry, no more complex than determining how much of a wall is shadowed when a ball is held before a lamp. We have a firm grasp of the star's size, thanks to several separate lines of evidence. Stellar models, which have been refined and validated over more than a century of astrophysics, establish a clear relationship between a star's size, its temperature, and its brightness. Through spectroscopic analysis, we can discern the star's temperature and its chemical makeup. The star's distance from us, determined with parallax and other methods, allows astronomers to translate its apparent brightness into its true, intrinsic luminosity. All of these independent measurements converge, painting a picture of a star approximately 1.85 times the diameter of our own Sunday. Knowing the star's dimensions and the percentage of light blocked during a transit, simple geometry reveals the planet's size. The calculation itself is direct and has been confirmed countless times with other planetary systems where more data is available. The result is a planet about 2.1 times the diameter of Jupiter, a measurement that stands on solid ground. The planet's mass, however, is determined using an entirely different approach. The radial velocity method measures the subtle wobble of the star caused by the planet's gravitational influence. As the planet completes its orbit, it gently tugs on its parent star, forcing the star to move in a tiny corresponding circle or ellipse. This movement induces a Doppler shift in the starlight, a minute change in the light's wavelengths that tells us how quickly the star is moving toward or away from Earth. The magnitude of this stellar wobble is dictated by the planet's mass and its proximity to the star. A planet with more mass will create a more pronounced wobble. A planet in a closer orbit will also produce a larger wobble, as the gravitational force is stronger over shorter distances. By carefully measuring this wobble and knowing the orbital distance from the transit timings, we can precisely calculate the planet's mass. What is remarkable is how these two distinct techniques, transits and radial velocities, provide results that align perfectly. The orbital period derived from the transit data is an exact match for the orbital period suggested by the radial velocity curve. The calculated mass and size are entirely consistent with the profile of a gas giant of exceptionally low density. Every piece of the puzzle fits. Similar methodologies have been repeatedly validated across numerous other star systems. Astronomers have compared transit data with direct imaging measurements where possible. They have employed asteroseismology, the analysis of stellar vibrations, to independently confirm the sizes of stars. Our techniques for measuring mass have been cross-checked against binary star systems, where masses can be measured directly through orbital dynamics. The science is both mature and dependable, giving us high confidence that this planet is indeed as large and as low density as the data suggests. Future observations promise to unveil much more about this distant giant. With the James Webb Space Telescope, astronomers are able to perform detailed spectroscopy on the planet's atmosphere as it transits. When the world passes before its star, the starlight filtering through its atmospheric layers will carry the chemical fingerprints of the molecules present. Water vapor, carbon dioxide, methane, sodium, potassium, titanium oxide, and vanadium oxide all leave unique absorption patterns in the light spectrum. By identifying these signatures, we can create an inventory of the atmosphere's composition. It may also be possible to map the atmosphere's temperature structure. Different atmospheric layers absorb and radiate light at distinct wavelengths. Through a meticulous analysis of the spectrum, scientists can construct a temperature profile, revealing how conditions change at various altitudes. This helps us understand the fundamental physics of how energy is transported through the planet. There is even the prospect of detecting signs of weather. If this world possesses large-scale atmospheric phenomena like storms, bands, or spots similar to Jupiter's Great Red Spot, they could introduce small variations in the transit light curves. Successive transits might appear slightly different as various regions of the atmosphere rotate into view. Detecting such variations would offer a first glimpse into this planet's dynamic climate. Telescopes on the ground can also contribute, as high-resolution spectroscopy can discern the Doppler shift of atmospheric gases as the planet orbits. This technique can identify molecules even when they produce very subtle spectral features. It can also be used to measure wind speeds by detecting the shift in spectral lines as gases move toward or away from us. Continued observation of this system could also reveal the presence of other planets. The majority of planetary systems contain more than one world. Our own solar system has 8, and some exoplanetary systems have 5, 6, or even more confirmed planets. If other worlds orbit this star, they might create their own transit dips or cause slight variations in the giant planet's orbital timing due to their gravitational tugs. There is even a possibility of finding moons. If this planet hosts large moons, they could produce their own distinct transit signatures. The detection of an exomoon would be a landmark discovery, opening up an entirely new class of celestial object for study. To date, No exomoons have been definitively confirmed despite extensive searches, but planets like this one, with their deep transits and long observational histories, represent the most promising places to look. The scientific investigation is far from over. Each new observation deepens our understanding, and every measurement helps to refine our models. This planet has been the subject of study for nearly a decade since its discovery was announced, and it will continue to be a focus for decades to come. The future will bring even more powerful instruments to bear. The European Extremely Large Telescope, now being built in Chile, will feature a mirror almost 130 feet in diameter. It will be capable of directly imaging some exoplanets and studying their atmospheres with unprecedented detail. The Nancy Grace Roman Space Telescope, planned for launch in the mid-2022, will hunt for exoplanets using gravitational microlensing, a method sensitive to planets far from their stars that other techniques often miss. Each new telescope and every new technique enriches our collective knowledge. This particular world, first found with relatively modest ground-based observatories, will be scrutinized by the most advanced instruments humanity has ever constructed. This is the very nature of science, where discoveries continually build upon one another. The pursuit of knowledge often reveals that every answer simply uncovers a new layer of mystery. It can be helpful to step back and reflect on the immense context of what we've come to understand. Before the year 1995, humanity knew of precisely 0 planets outside of our own solar system. There were compelling theories, a great deal of speculation, and fervent hopes, but not a single confirmed world. Today, only a few decades later, that number has soared to over 5,700 confirmed exoplanets, with thousands of additional candidates awaiting verification. This exploration has revealed a stunning variety of worlds, covering every conceivable type. We have catalogued rocky planets smaller than our own Earth and gas giants that dwarf Jupiter. We have seen planets that complete a full orbit around their star in a matter of hours, and others that require centuries to make the same journey. Discoveries include planets situated within the habitable zones of their stars, where conditions might allow for liquid water to exist on a solid surface. We have found worlds in binary star systems, where 2 suns would hang in the sky. Some planets orbit so close to their stellar hosts that their surfaces are perpetually molten oceans of rock. And we have even identified rogue planets, adrift in the cosmos, wandering through interstellar space without a parent star. The sheer volume of these discoveries has taught us a fundamental lesson. Planetary systems are not a rarity, but a common feature of the universe. It is now thought that nearly every star you can see in the night sky is likely to host at least one planet. Our own galaxy, the Milky Way, is estimated to contain somewhere between 100 billion and 400 billion stars. If the vast majority of those stars have planets, then the number of worlds in our galaxy alone likely numbers in the hundreds of billions. When we consider that there are at least 2 trillion other galaxies in the observable universe, the total count of planets becomes a figure that is nearly impossible to truly comprehend. Somewhere within that staggering census of worlds, life might exist. This possibility is one of the most powerful motivations driving exoplanet research. The goal is often to find Earth-like planets, worlds that possess the necessary conditions for life as we understand it. This particular giant world, however, is not such a place. It is a gas giant, meaning it has no solid surface to stand on. It endures temperatures that would obliterate any form of life we can imagine, and its atmosphere is a composition of hydrogen and other exotic vapors. Life, as we know it, simply could not survive in such an environment. Yet, studying planets like this one is crucial for our understanding of planetary systems as a whole. Objects like this, known as hot Jupiters, probably did not form in the orbits where we observe them today. The prevailing theory is that they formed much farther out in their planetary systems and subsequently migrated inward over millions of years. This process of migration can have a profound and dramatic effect on an entire system, potentially pushing smaller planets into different orbits or even ejecting them completely. By understanding how hot Jupiters form and migrate, we gain insight into which kinds of planetary systems might be more hospitable to life. If this inward migration is a common and violent event, it could mean that the inner regions of many systems are cleared out, destroying any Earth-like planets that might have otherwise formed there. Conversely, if the migration is a rare or more gentle process, it would increase the chances that more systems could harbor rocky worlds in their habitable zones. This discovery is therefore a single, vital piece of a much larger puzzle, a data point that helps us map the incredible diversity of planetary systems throughout the cosmos. What would it be like to actually visit this world? While such a voyage is completely beyond our current technological reach, the journey itself would present a challenge far greater than anything humanity has ever undertaken. The planet is over 1,000 light-years away, meaning that a craft traveling at the speed of the Voyager 1 probe, about 17 kilometers per second, would take more than 11 million years to arrive. That span of time is longer than modern humans have existed as a species. But if we could imagine making the journey instantaneously, as in a work of science fiction, what would we see? As we approached the system, the first thing to stand out would be the star itself. It is hotter and more luminous than our Sun, appearing as an intensely white point of light, perhaps with a subtle bluish hue. Its radiation output is significantly higher, bathing the entire planetary system in powerful energy. Drawing closer to the giant planet, its immense scale would become apparent. From 1,000,000 miles away, it would resolve into a distinct disk. At a distance of 100,000 miles, it would dominate the view, a vast, curved horizon stretching across the visual field. The colors would likely be unlike anything found in our solar system. Jupiter has its characteristic bands of brown, tan, cream, and rusty red, which are created by different chemical compounds at various altitudes, stretched into parallel stripes by the planet's swift rotation. This world might exhibit similar banding, or it could appear more uniform in color, or it might even display atmospheric patterns we have never witnessed before. If it were somehow possible to descend into the atmosphere, the conditions would grow increasingly extreme. Temperatures near the cloud tops are already severe. With greater depth, the pressure would mount relentlessly. The atmosphere would become progressively denser, and the light from the star would dim into a perpetual twilight before fading into complete darkness. There is no surface on which to land. Unlike rocky planets, which have a distinct solid crust, gas giants are composed almost entirely of gas and fluid. As one descends, the atmosphere simply gets thicker and hotter. Eventually, the pressure becomes so intense that the very distinction between gas and liquid dissolves. You would find yourself immersed in a supercritical fluid, a strange phase of matter that has properties of both a gas and a liquid. Deeper still, if survival against the crushing pressure and searing heat were possible, one might encounter even stranger phenomena. In the cores of some gas giants, hydrogen is compressed so tightly that it behaves like a metal. Whether this particular world has such a layer is unknown. Its exceptionally low density suggests that whatever core it possesses must be either small or diffuse. Understanding the internal structure of this world is one of the primary challenges in studying it. We cannot see inside it directly. We can only measure the planet's total mass, its size, and its behavior, and from these observations, we can infer what might be happening deep within its interior. Different scientific models offer different predictions, and perhaps future observations will help us determine which is most accurate. This giant planet is part of a broader lesson that modern astronomy has taught us. The universe is far stranger and more varied than we ever imagined when our own solar system was our only example. Every type of planet we thought we understood has revealed variations we never anticipated. Gas giants can be cold and distant from their stars, like Jupiter and Saturn, or they can be scorching hot and in tight orbits, like the hot Jupiters. They can be dense and compact or puffy and inflated. They can exist alone or have companions. Their histories can include migration, collisions, or even ejection into the lonely void of interstellar space. Similarly, rocky planets can be smaller than Earth or several times larger. These distant worlds can be arid, barren landscapes, or they might be completely submerged in water. Some are veiled by dense atmospheres of carbon dioxide or nitrogen, while others are shrouded in more exotic gases. Their orbits vary immensely, placing them within the habitable zone, much nearer to their stars or significantly farther away. Even ice giants, similar to our own Uranus and Neptune, exhibit their own unique variations. Some exoplanets appear to be true water worlds, with vast, deep oceans concealing rocky cores. Others could be composed primarily of carbon, their surfaces potentially covered in diamond, forged under immense pressures. The variety among these worlds is astonishing, and with every new instrument or technique we pioneer, we uncover phenomena we never anticipated. The universe, it seems, consistently holds new surprises for us, and this recent discovery is a perfect example of that ongoing revelation. It concerns the largest confirmed planet ever found, a world so profoundly inflated that it would float in water, despite being more massive than any other known planet. This is a powerful illustration of the strange outcomes that arise when the laws of planetary physics are pushed to their absolute limits. The search for exoplanets stands as one of the great modern adventures of humanity. In the span of just a few decades, we have transitioned from knowing only the planets of our solar system to cataloging thousands of worlds orbiting other suns. We have pioneered methods to analyze the atmospheric composition of planets that are light years distant. We have located worlds within the habitable zones of their stars, places where liquid water could potentially pool on the surface. Our fundamental understanding of what a planet can be and how it comes into existence has been profoundly expanded. This particular discovery represents a significant landmark on that continuing journey. While it currently holds the record for the largest planet by radius, its importance extends far beyond that distinction. It is a world that instructs us on the sheer diversity of planetary systems, the complex processes that mold gas giants, and the incredible extremes the cosmos can produce. This is a good moment to address a question that frequently surfaces during discussions of such discoveries. Some people reasonably ask about the point of it all, questioning why we invest time and resources into studying a planet we can never visit, touch, or experience firsthand. These are valid inquiries that merit a thoughtful response. First, there is the innate human desire for understanding. We are an inherently curious species, driven to make sense of our surroundings, which includes the vast universe beyond our own world. This very curiosity has been the engine behind every major scientific breakthrough in history. The same impulse that leads us to wonder about a distant gas giant is the one that ultimately resulted in every piece of technology we use and every medicine that safeguards our health. Knowledge possesses an intrinsic value. A deeper comprehension of the universe is its own reward, independent of any immediate practical use. When we learn about a giant planet around a faraway star, we contribute to the collective sum of human knowledge, and that in itself is valuable. Second, the study of exoplanets illuminates the principles of planetary physics in a way that observing our solar system alone never could. We have only a single solar system to examine in detail, and it presents a very specific arrangement of planets. We might assume Jupiter is the template for all gas giants, but without a wider sample, we cannot discern which of its characteristics are universal and which are unique to its own history and environment. Exoplanets provide that crucial, broader context. By analyzing hundreds of gas giants across a multitude of different systems, we learn which traits are common and which are rare. We encounter phenomena, such as extreme planetary inflation, that are absent in our own cosmic neighborhood. This allows us to test our theories against a much richer dataset, making our grasp of planetary science more robust and complete. Third, the technologies created for exoplanet research frequently find wider applications. The techniques for measuring incredibly subtle dips in starlight have uses in fields like medical imaging, precision manufacturing, and quality control. Throughout history, basic scientific research has often led to unforeseen practical advantages. Fourth, and perhaps most significantly, investigating exoplanets is a vital part of the grander quest to comprehend our own place in the cosmos. Are we alone? Is our Earth a unique phenomenon? Or do other, similar worlds exist? Could life have arisen elsewhere? These are among the most profound questions humanity has ever posed. Exoplanet research is steadily moving us closer to the answers. This specific giant planet is not a candidate for life, but understanding worlds like it helps us grasp the nature of planetary systems as a whole. It aids us in identifying which kinds of systems are more likely to harbor habitable planets and which are not. Every single piece of this cosmic puzzle is important. There is also immense value in inspiring the next generation. Young people today are growing up in an era where thousands of exoplanets are a known reality, where astronomers can probe the skies of distant worlds, and where the search for extraterrestrial life is an active scientific endeavor rather than mere speculation. Some of these young people will become the scientists who achieve the next great breakthroughs. They will construct the telescopes that see deeper into space, develop the methods that reveal more about faraway worlds, and ask the questions we haven't yet conceived. Inspiring them by showing them a universe filled with wonders awaiting discovery is a worthy outcome of this research. This planet is one such wonder, a world that defies our models and stretches our comprehension of what is possible. Every child who learns of its existence is reminded that the universe is larger and stranger than they ever imagined. Every single atom in your body was once inside a star. The carbon that forms your cells, the oxygen you inhale, the iron in your blood, all of it was forged in the hearts of stars that perished billions of years ago. When those stars exploded, they scattered these newly created atoms across space. For eons, these atoms drifted through the cosmos until they eventually coalesced to form our solar system, our planet, and, in time, you. The substance of your body is, in a very real sense, stardust. This is not a poetic metaphor. It is a literal scientific fact. The elements heavier than hydrogen and helium that are essential for life could only have been created in the intense heat and pressure of stellar cores and supernovae. And the giant planet we have been considering is made of that very same material. Its hydrogen atoms are identical to those in a molecule of water. Its helium atoms are the same as those that fill birthday balloons. On the most fundamental level, there is no distinction between the matter that constitutes this remote world and the matter that constitutes you. Our connection to the cosmos is not just through observation and intellect, but through our very physical being. We are not merely observers of the universe, we are an intrinsic part of it. When we observe planets in the distant cosmos, we are in a very real sense examining our own story, or at least the fundamental materials and physical laws that allowed for our existence. This may be the most profound insight offered by modern astronomy. We are not merely observers of some far-off spectacle. We are integral participants in a cosmic narrative that began with the Big Bang and unfolds to this day. The very same principles of physics that direct the behavior of colossal gas giants also orchestrate the functions of the cells within our own bodies. The gravitational force that binds planets to their stars is the same force that anchors us to the surface of Earth. Grasping this deep connection fundamentally alters one's perception of the world. It makes the universe feel less remote, less disconnected from our daily lives. This understanding reveals that all things are part of a single, vast, and interconnected whole. So, as you return to your everyday routine, try to carry a piece of this perspective with you. Remember that somewhere, more than 1,000 light-years from here, a planet double the size of Jupiter is tracing its orbit around a star. It existed long before humans walked the Earth and will continue its silent journey long after we are gone. That world has no awareness of us, nor does it have any reason to care, yet we are aware of it. We find it compelling, and through that knowledge and that curiosity, we manage to transcend our own small corner of the universe, even if just for a fleeting moment. Humanity is currently living through a unique period in its history. We represent the first generation to know with certainty that other worlds circle other suns. We are the first to begin the great work of cataloging the planets of other solar systems. We are also the first to analyze the atmospheres of worlds we can never hope to visit in person. This newfound knowledge reshapes how we view our own place in the cosmos. We are not isolated in a universe of sterile stars. Instead, we are part of a cosmos that is filled with an abundance of worlds. Many of these planets are unlike anything we have ever experienced. Some of them, however, might be similar enough to our own to potentially support life. The universe is waiting for us. It has, in fact, always been waiting. And now, finally, we are starting our exploration. I appreciate you joining me for this exploration. If you found this journey meaningful, please think about supporting this channel. Every like, every subscription, and every share enables me to continue creating these in-depth examinations of the cosmos. When you have the opportunity, look up at the night sky. Contemplate the planets that might be orbiting those distant points of light. Allow yourself to wonder about what is truly out there. That sense of wonder, that deep curiosity, and that openness to the immense unknown are among the finest qualities that we as a species possess. Good night, and may your view of the stars be forever changed. Before we conclude, however, some additional history makes this particular discovery all the more remarkable. The story of how we first learned to detect planets around other stars is a narrative of persistence, human ingenuity, and numerous failures that preceded ultimate success. For many decades, astronomers attempted every method they could devise, and for just as long, their efforts yielded nothing. During the 1,940 seconds and 50 seconds, a few astronomers made claims of discovering planets orbiting nearby stars through a technique known as astrometry, which entails measuring the minuscule wobbles in a star's position as it traverses the sky. The most well-known of these claims centered on Barnard's star, one of the closest stars to our own solar system. Peter van der Kamp, a Dutch astronomer working in Pennsylvania, dedicated decades to gathering data and ultimately declared that Barnard's star was host to two planets similar in size to Jupiter. His declaration sparked a wave of tremendous excitement. The implication was that if even the nearest stars had planets, then planets must be a common feature of the galaxy. But as other scientists tried to confirm his work with different instruments, they were unable to replicate his findings. It slowly became apparent that the wobbles van der Kamp had observed were not caused by planets at all, but rather by mechanical adjustments made to the telescope he used. Each time the instrument was modified or serviced, it introduced tiny, systematic errors that perfectly mimicked the signature of an orbiting world. Peter van der Kamp never conceded that his planets were not real. He continued to defend his conclusions until his death in 1995. The very same year, the first confirmed exoplanet around a sun-like star was officially announced. He missed, by only a matter of months, the vindication that planets truly do orbit other stars, though not the specific one he had so diligently studied. This cautionary episode cast a long shadow over the field for decades. Astronomers grew exceptionally cautious about making claims of planetary detections. They began to require multiple, independent confirmations using a variety of methods. They meticulously investigated every conceivable source of systematic error. The false positive associated with Barnard's star had taught them a hard lesson about how easily one could be misled by the data. This is precisely why the 1995 announcement of 51 Pegasi b was so thoroughly vetted. Michel Mayor and Didier Queloz had found the planet using the radial velocity method, which measures the Doppler shift in a star's light as it moves slightly toward and away from us. They were well aware, however, that other stellar phenomena could produce a similar signal. Pulsations on the star's surface, large star spots, or even an unseen companion star could all create patterns that looked like a planet. They spent months collecting data, constantly checking and rechecking their analysis. They searched for any correlation with the star's activity cycles, which might suggest the signal originated from the star itself. They calculated their margins of error again and again. They only went public with their findings when they were absolutely certain that no other explanation could account for what they had observed. Even after their announcement, there was some skepticism. Jeffrey, Marcy, and Paul Butler, a pair of American astronomers who had been searching for exoplanets with similar techniques, were initially doubtful of the result. A planet with the mass of Jupiter completing an orbit in only 4 days seemed physically implausible. Yet, when they directed their own instruments toward 51 Pegasi, they confirmed the existence of the planet within a matter of days. The world was undeniably real. This culture of meticulous verification continues to define exoplanet science today. When the HatNet survey first detected the transit of the giant planet we have been focused on this evening, they did not rush to announce a discovery. Instead, they gathered more information. They performed follow-up observations using larger telescopes. They measured the star's radial velocity to confirm that a massive object was indeed in orbit. They checked for any sign that the signal could be an artifact or something other than a planet. Only after this entire battery of checks was completed, years after the initial detection, did they finally announce their find. It is this painstaking approach that gives us such strong confidence in the results. The planet is real because multiple, independent lines of evidence all point to the very same conclusion. This history of careful science, of false starts leading to eventual triumph, and of the immense effort needed to distinguish genuine discoveries from instrumental errors, is part of what makes the study of exoplanets so compelling. It is a profoundly difficult endeavor. The process of discovery calls for patience, a deep sense of rigor, and an openness to being proven wrong. But when a finding withstands that level of scrutiny, it becomes something we can trust. Other planets that hold records in their own right offer essential context and a basis for comparison with this particular discovery. The most intensely hot exoplanet known is Kelt 9b, a world we have touched upon before. Its dayside temperature climbs beyond 4,300 Kelvin, or approximately 7,600 degrees Fahrenheit, a reading that is hotter than the surface of many stars. In these extreme conditions, molecules cannot hold together and are torn apart into their constituent atoms. The atmosphere is a haze of atomic hydrogen, helium, iron, and magnesium, all drifting as individual particles rather than being bound into molecular structures. Kelt 9b is so profoundly hot that it is in a state of slow evaporation, its mass bleeding into space as its atmosphere is steadily stripped away. On the other end of the spectrum, the coldest known exoplanet is more difficult to identify, as frigid worlds are exceptionally challenging to detect. However, a planet found in 2005 through gravitational microlensing, OGLE 2005 BLG390LB, is estimated to have a surface temperature around 50 Kelvin, or about -364 degrees Fahrenheit. This is a temperature even colder than that of Pluto. It follows a distant path around its host, a small red dwarf star from which it receives very little warmth, making it almost certainly a frozen and lifeless world. The densest known exoplanet is a subject of ongoing discussion, but one of the leading candidates is Kepler 131c, which could possess a density greater than 30 grams per cubic centimeter. For perspective, The density of iron is about 7.9 grams per cubic centimeter, while lead is around 11.3. A world with a density exceeding 30 would need to be made of something truly unusual, perhaps heavy elements compressed under immense pressure. The mechanisms that could form such incredibly dense planets are not yet well understood. The least dense exoplanet known, apart from the giant that is our focus, is WASP 193b, which has a density of about 0.059 grams per cubic centimeter. This value is only slightly less than that of our record holder. The remarkable similarity in the puffiness of these two planets highlights a central question in current research: why some hot Jupiters inflate to such enormous sizes while others of similar mass stay more compact. The record for the shortest confirmed orbital period belongs to K2137b, which circles its main sequence star in only 4.3 hours. This means it completes more than 5 full orbits in the time it takes for one Earth day to pass, tracing its path at tremendous speed. Being so close to its star, it is almost certainly tidally locked, with one hemisphere enduring a perpetual roasting, while the opposite side is cast in permanent darkness. Determining the planet with the longest orbital period is far more challenging because worlds in such wide orbits are very difficult to find. Their transits are infrequent, if they happen at all, and their gravitational tug on their host stars is faint. Still, some planets that have been directly imaged orbit at distances of hundreds or even thousands of astronomical units, requiring thousands of years to complete a single revolution. These remote giants likely formed through a different process than planets closer in, possibly from a direct gravitational collapse of gas and dust, rather than through core accretion. Each of these extreme worlds offers a unique lesson. The hottest planets reveal how atmospheres behave at temperatures that sunder molecules. The coldest planets illustrate what occurs when a world is deprived of nearly all stellar energy. The densest worlds push the limits of our models for planetary interiors, and the least dense planets, like the one we are examining, challenge our grasp of atmospheric physics and the transport of energy. Taken together, these record holders help to define the very boundaries of what is possible for a planet. They represent the far edges of the planetary population, the extremes of the distribution. Understanding these outliers is crucial because they place constraints on our theories. Any comprehensive model of planet formation and evolution must successfully account for not only the typical planets, but also these exceptional cases. The host star itself warrants a closer look, as the star's properties are fundamental to understanding its planet. F-type stars, such as this one, hold a specific place within the stellar classification system. They are more massive than our own Sun, which is a G-type star, but less massive than A-type stars. Their surfaces are hotter, with temperatures ranging from about 6,000 to 7,500 Kelvin, compared to our Sun's 5,800 Kelvin. They are also more luminous, radiating several times more energy than our stellar neighbor, but this comes at the cost of a shorter lifespan. The more massive a star, the more rapidly it consumes its nuclear fuel. Our Sun is expected to last for about 10 billion years in its main sequence, the stable phase where it burns hydrogen. An F-type star like this one may only last for 5 to 7 billion years. At the conclusion of its life, it will swell into a red giant, an event that could engulf any planets in close orbit. F-type stars are compelling targets in the search for exoplanets because they are bright enough to be studied in detail, yet not so hot that their intense radiation washes out the faint signals from a planet. They are also relatively common, constituting perhaps 3% of all stars in our galaxy. While that percentage might seem small, in a Milky Way containing hundreds of billions of stars, it still amounts to billions of F-type systems. The rotation rate of this specific star is also a relevant detail. Stars that spin rapidly are more difficult to analyze with the radial velocity method, as their rotation broadens and blurs the spectral lines. This star rotates at a relatively slow pace, which simplified the task of measuring the tiny Doppler shifts induced by its orbiting planet. The star's chemical makeup, especially its metallicity, a term astronomers use for the abundance of elements heavier than helium, can also shape planet formation. Stars with higher metallicity are observed to host more giant planets, likely because more solid material was available in the protoplanetary disk to build planetary cores. This particular star has a metallicity similar to our Sun's. Every one of these stellar characteristics plays a role in our understanding of the planetary system. The star's luminosity dictates the amount of energy the planet receives. Its age provides a timeline for the planet's evolution. Its rotation and activity levels affect how readily we can detect and characterize the planet. Stars and their planets are bound in an intimate connection. To comprehend one, we must also comprehend the other. Over the last decade, theoretical models have attempted to explain the existence of inflated hot Jupiters like this one. When the first of these puffy worlds were discovered, they presented an immediate puzzle. Standard models of planetary structure had predicted that a gas giant of a certain mass should have a corresponding size. Jupiter, for instance, aligns very closely with the predicted size for a planet of its mass and age. But these newly found hot Jupiters were simply too large. Some unknown mechanism was causing them to swell far beyond what the models had allowed. The most immediate explanation for these planets' condition was the intense heat from their stars. These worlds orbit so closely that they are saturated with hundreds or thousands of times more radiation than Jupiter receives from our own Sun. This immense energy heats the upper atmosphere, which in turn causes it to expand. While simple models that account for this heating can explain some of the inflation, they fall short in the most extreme cases, including that of our record-holding planet. The planets are simply more puffed up than even detailed models predict, which suggests that something else must be at play. One of the leading theories points to the transport of heat from the irradiated upper atmosphere down into the planet's deep interior. In standard models, the energy that reaches the upper atmosphere is mostly radiated back into space, never penetrating very far. But if some mechanism were able to channel a fraction of that energy deep inside the planet, it would effectively inflate the world from within. This leads to a compelling question. What could cause such deep heating? One possibility is a process called ohmic dissipation. The star's powerful radiation ionizes the upper atmosphere, which creates a layer that can conduct electricity. As atmospheric winds move this conductive material through the planet's magnetic field, electrical currents are induced. These currents then dissipate their energy as heat far beneath the surface, keeping the interior hot and inflated. Another potential explanation involves the intricate coupling between the circulation in the atmosphere and the dynamics of the interior. An extreme temperature difference between the day and night sides of these planets drives powerful atmospheric flows. It is thought that these flows could interact with deeper layers, transferring angular momentum and energy in complex ways that prevent the interior from cooling and contracting as it otherwise would. A third possibility is that these planets have unusual atmospheric compositions that change how efficiently they radiate energy away. If specific molecular species at certain altitudes absorb and re-emit radiation in ways that trap heat, the planet could maintain a much higher internal temperature than expected. Recent work has suggested that the truth may be a combination of all these mechanisms, with different factors being more or less significant for different planets based on their unique properties. The scientific community is still working to develop a single, unified understanding. Computer simulations are a central component of this research. Scientists build detailed, three-dimensional models of planetary atmospheres to track how energy flows, how winds form, and how chemistry evolves over time. They also simulate the interiors of these worlds, modeling the transport of heat from the core to the surface and how the planet's structure responds to external heating. By comparing these simulations to observational data, they can test which theoretical mechanisms best fit the evidence. The record-holding planet is an especially valuable test case for these simulations because it is so extreme. Any theory that can successfully explain typical hot Jupiters must also be able to account for this outlier. If a model is unable to reproduce the extreme inflation that we observe, it means something important is missing from it. This discovery also has a connection to our search for life elsewhere in the universe. At first glance, the connection is indirect, as this giant planet seems irrelevant to the search for life. It is, after all, a gas giant with no solid surface, and its temperatures would annihilate any organic molecules. Its atmosphere is composed of hydrogen and exotic vapors, not the oxygen and water we associate with living things. No form of life as we know it could possibly survive there. The discovery is, however, relevant in more subtle ways. Understanding how planetary systems form and evolve helps us to identify which systems are more likely to harbor habitable planets and which are not. Hot Jupiters like this one probably formed much farther away from their stars and then migrated inward. Such a migration would have been catastrophic for any smaller planets in the inner solar system. Any rocky worlds in the habitable zone would have been scattered, ejected, or even swallowed as the giant plowed through the system. If the migration of hot Jupiters is a common event, then many planetary systems may have been sterilized by these migrating giants. The inner regions that might have otherwise hosted Earth-like planets were instead disrupted by the passage of these massive worlds. Our own solar system, notably, does not have a hot Jupiter. Jupiter and Saturn formed in the outer solar system and remained there. This stability may have been a necessary condition for the emergence of life on Earth. Had Jupiter migrated inward early in our solar system's history, it might have scattered the material that eventually formed Earth, preventing our own planet from ever existing. Gaining a better understanding of the factors that determine whether gas giants migrate helps us identify which types of systems are most likely to be habitable. Stars of certain masses, with specific metallicities, and in particular galactic environments, may be more or less likely to host stable planetary systems. This knowledge helps to guide the search for Earth-like planets. There is also a broader lesson to be learned here, that planetary systems can look profoundly different from our own. For decades, astronomers operated under the assumption that other solar systems would resemble ours, with small, rocky planets close to the star and gas giants farther out. The discovery of hot Jupiters shattered that assumption. They revealed that planets can end up in configurations we had never imagined. This opens our minds to possibilities we might have otherwise dismissed. Perhaps habitable planets exist in unexpected places. Perhaps there are forms of life that do not require the conditions we currently consider essential. Perhaps the universe is even stranger than we think. By cataloging the sheer diversity of planetary systems, we expand our conception of what is possible. We become more creative in our thinking about where life might exist. We begin to consider scenarios that would not have occurred to us if we only knew our own solar system. The more we learn about planets like this distant giant, the better our understanding becomes of the full range of possibilities. And that understanding, even when it involves inhospitable worlds, ultimately serves the search for life. Since the announcement in 2017, astronomers have aimed many different instruments at this star to learn more about its giant planet. Ground-based telescopes have refined measurements of the transit's depth and timing. Space-based observatories have searched for variations that might indicate the presence of additional planets or moons. Spectrographs have been used to probe the atmosphere for chemical signatures. The Hubble Space Telescope has observed transits of this planet, searching for water vapor and other molecules in its upper atmosphere. These observations are challenging because the signal is incredibly small, but Hubble's stability and sensitivity make it uniquely well-suited for the task. Before its mission concluded in 2020, the Spitzer Space Telescope turned its infrared gaze upon this planet. Observations in the infrared are especially revealing for hot Jupiters. as this light probes different strata of the atmosphere than visible light can reach. The data from Spitzer provided crucial constraints on the thermal structure of the atmosphere, shedding light on the efficiency of heat transport from the intensely hot day side to the permanent night side. Now, the James Webb Space Telescope is poised to carry exoplanet characterization to an entirely new level. JWST has already demonstrated an extraordinary capacity for detecting specific molecules within exoplanet atmospheres, and with a precision never before achieved. When it eventually observes this gas giant, it will surely unveil intricate details about its atmospheric composition, its temperature profiles, and possibly even the signatures of complex weather patterns. Observatories on Earth also continue to make vital contributions to this work. High-resolution spectrographs are capable of detecting the individual spectral lines from molecules in the atmosphere, which reveals not only their presence but also their motion. By carefully measuring the Doppler shifts in these lines, astronomers can begin to map the patterns of wind, tracking how gas circulates from day to night and flows between the equator and the poles. Elsewhere, photometric monitoring involves searching for subtle variations in the depth or timing of a transit, which could signal the existence of other bodies in the system. A moon in orbit around the giant planet would create a very distinct signature, as would another planet gravitationally perturbing its path. To date, no such signals have been found, but the search is ongoing. The wealth of data accumulated from all these observations has steadily refined our portrait of this world. The measurement of its mass, for instance, has improved from an initial estimate of roughly 1/3 of Jupiter's mass to the current best value of about 0.45 Jupiter masses. Its radius has been measured with greater precision, and its orbital parameters have been determined with much higher accuracy. This gradual sharpening of focus is the very nature of scientific progress. Each new observation contributes another piece to the puzzle. The uncertainties in our measurements diminish, and the overall picture grows clearer. What began as a faint, fuzzy detection slowly transforms into a well-characterized world. This process is certain to continue for many years. Future telescopes will provide data of even higher quality, while new analytical techniques will extract more information from observations already made. Our understanding of this particular planet will continue to grow, and what we learn from this extreme example will eventually be applied to other planetary systems. The lessons gained from studying this case will inform how we investigate more moderate worlds. The techniques developed to probe this intense atmosphere will be refined for use on smaller, cooler planets, perhaps one day even on Earth-like planets within their stars' habitable zones. This is the fundamental trajectory of science, where each discovery paves the way for the next, and every new technique opens up unforeseen possibilities. What may seem like a destination is, in reality, just a new point of departure. The transit method is a surprisingly potent tool, not only for discovering planets but also for characterizing them in exquisite detail. When a planet crosses in front of its star, it does much more than simply block a bit of starlight. The precise pattern of that dimming encodes a vast amount of information about the planet's size, its orbit, and even its atmosphere. The depth of the transit, or how much the starlight dims, indicates the size ratio between the planet and its star. A larger planet will naturally block more light. By measuring this depth precisely, astronomers can calculate the planet's radius relative to that of its star. If the star's size is already known from other observations, the planet's true physical size can be determined. The duration of the transit provides information about the orbital geometry. A crossing that passes over the star's equator will last longer than a grazing transit that merely clips the star's upper or lower edge. By measuring this duration and comparing it to the orbital period, scientists can constrain the orbit's inclination and the impact parameter, which describes how close the planet passes to the star's center. The very shape of the transit light curve, The way the brightness changes as the planet enters and exits the stellar disk reveals still more. Stars are not uniformly bright across their visible surfaces. They appear brighter at the center and dimmer toward their edges, an effect known as limb darkening. The transit light curve is molded by this limb darkening, and by modeling it with care, astronomers can learn about properties of both the star and the planet. Transmission spectroscopy takes this analysis a step further. By observing a transit across many different wavelengths, it is possible to measure how the transit's depth changes with color. If a planet has an atmosphere containing molecules that absorb specific wavelengths of light, the planet will appear slightly larger at those wavelengths because its atmosphere is effectively opaque there. Mapping these variations allows for the identification of the molecules present. Complementary information comes from eclipse spectroscopy. This technique focuses on the moment the planet passes behind its star, causing its own light to disappear from our view. By comparing observations taken during the eclipse to those taken just before or after, astronomers can isolate the light coming from the planet itself. This reveals information about the planet's temperature, the composition of its day-side atmosphere, and how efficiently heat is redistributed around the globe. Phase curves track the subtle changes in a planet's brightness over the course of its entire orbit. As the planet travels around its star, we see different illuminated portions of its surface. The day side is at its brightest when the planet is on the far side of its orbit, presenting a fully illuminated face toward us. By measuring these brightness variations, astronomers can map the temperature distribution across the planet's surface and track its atmospheric dynamics. All of these powerful techniques have been applied to hot Jupiters like our record holder. Used in concert, they build a remarkably detailed picture of worlds we have never visited and never will. From simple patterns of light, we can deduce sizes, masses, temperatures, compositions, and even wind patterns. This is the power of precision measurement. Through careful observation and clever analysis, we can learn a great deal about objects far beyond our direct reach. The future of exoplanet science is extraordinarily bright. New missions are being planned that will discover thousands of additional planets. New telescopes will characterize their atmospheres with unprecedented detail, and new techniques will enable observations that seem impossible today. The Plato mission, scheduled for launch in 2026, will search for Earth-like planets orbiting Sun-like stars. It is designed to find planets in the habitable zones of stars similar to our own, providing prime targets for follow-up observations in the search for signs of life. The Atmospheric Remote Sensing Infrared Exoplanet, Large Survey, or ARIEL, is planned to launch in 2029 with the goal of studying the atmospheres of approximately 1,000 exoplanets. This work will help assemble a statistical portrait of how atmospheric characteristics change from one type of planet to another, providing essential context for understanding individual discoveries like the record-holding giant we have explored. On Earth, a new generation of extremely large telescopes currently under construction is poised to transform the direct imaging of exoplanets. It is possible these observatories will be capable of seeing Earth-like worlds orbiting nearby stars, capturing direct photons from planets that could potentially harbor life. These future breakthroughs will stand upon the foundation of everything we have learned so far. The hot Jupiters being identified today are helping to prepare the way for the discovery of Earth-like planets in the future, as the very techniques being honed on these massive worlds will one day be adapted for smaller, more difficult targets. Science is an inherently cumulative process, where each new finding provides the bedrock for the next one. The colossal planet that has been our focus is an integral part of this continuing endeavor, representing another step along the journey toward comprehending planetary systems in their full and astonishing diversity. It is conceivable that one day we will locate a planet exhibiting indications of life, perhaps a particular atmospheric signature or a state of chemical disequilibrium, something not easily accounted for by geology or chemistry alone. Such a discovery would fundamentally alter our perception of our own place within the cosmos. When that moment arrives, it will be the culmination of decades of effort spent characterizing planets of every variety. The hot Jupiters, the super-Earths, the mini-Neptunes, and the inflated giants will all have contributed to the base of knowledge that enabled such a profound revelation. Even the most bizarre and least hospitable worlds offer lessons that are of great importance. This reflects the fundamental nature of scientific inquiry. It is impossible to predict which finding will prove to be significant. There is no way to know which method developed for one application will become indispensable for another. One simply follows the trail of curiosity, trusting that the pursuit of understanding is a worthy goal in itself. This enormous planet is a component of that magnificent project, a single world among thousands already catalogued and countless millions that await detection. It holds a record today that might be broken tomorrow, a puzzle that could one day be completely solved or might forever retain an element of mystery. Yet regardless of the outcome, what truly matters is that we searched, that we found it, and that we made the attempt to comprehend it. The universe is immense and largely uncharted, but every fragment of knowledge we acquire represents a victory. Before concluding, it is worth exploring a few more compelling dimensions of this specific discovery. The constellation Hercules, the location of this star system, has been a subject of observation since antiquity. The ancient Greeks bestowed upon it the name of their legendary hero, a figure of immense strength who performed 12 seemingly impossible labors. This constellation also hosts some remarkable deep sky objects, among them Messier 13, which is one of the most brilliant globular clusters observable in the northern hemisphere. Globular clusters are ancient, tightly packed spherical swarms of hundreds of thousands of stars, acting as primordial relics that orbit our own galaxy. The Greeks, of course, had no awareness of the planet circling this particular star in Hercules. They were not even aware that stars were actually distant suns. In their cosmology, the stars were merely points of light affixed to a celestial sphere that revolved around the Earth. The notion that stars might possess their own families of planets would have been nearly inconceivable to them. Our current perspective required millennia of accumulated insight to achieve. Copernicus was the one who shifted Earth from its central position in the universe. Galileo aimed his telescope toward the heavens and witnessed moons circling Jupiter, demonstrating that not everything revolved around our world. Newton provided the mathematical explanation for gravity, which gave us the ability to compute orbits and forecast celestial positions. The technique of spectroscopy later unveiled the chemical composition of the stars, while relativity subsequently refined our conception of space and time. Then, in the 1990 seconds, we finally engineered instruments with enough precision to sense the presence of planets around other stars. Each of these steps was built upon the ones that preceded it, as every generation of scientists inherited the knowledge and the instruments of their forerunners and advanced the frontier a little more. The detection of this giant planet is a direct consequence of that cumulative exertion, representing centuries of dedication from thousands of individuals who posed questions and pursued answers. This historical context is valuable to remember, as scientific breakthroughs do not materialize out of thin air but are the culmination of extensive chains of inquiry, with every link relying on those that came before it. When we commemorate a discovery of this nature, we are, in a deeper sense, honoring the entire scientific structure that made it achievable. The idea of the habitable zone is connected to hot Jupiters in significant and often unappreciated ways that merit a closer look. This zone is defined as the orbital region around a star where conditions could potentially permit liquid water to exist on a planet's surface. If a planet is too close to its star, any water will vaporize. If it is too distant, that water will be locked away as solid ice. Only within this intermediate area can liquid water endure, a condition widely believed to be essential for life as we understand it. The precise dimensions of any given habitable zone are determined by a multitude of factors, with a star's luminosity being the most critical variable. Brighter stars possess habitable zones that are wider and farther out. However, a planet's atmosphere also plays a crucial role. A dense atmosphere rich in greenhouse gases can insulate a planet, keeping it warm even if it receives less energy from its star. In contrast, a world with a thin atmosphere, or one lacking greenhouse gases, might remain too cold despite being situated within the traditionally defined habitable zone. Hot Jupiters, much like the record holder we've examined, orbit their stars far inside this zone. They are immensely too hot for liquid water, but their study provides critical insights into how planets migrate within their systems and which orbital arrangements are stable. If a system contains a hot Jupiter, its habitable zone has very likely been disturbed. Any small, rocky worlds that might have once formed there were probably scattered or ejected from the system entirely as the gas giant migrated inward. This suggests that systems with hot Jupiters are unlikely to be promising locations for finding Earth-like planets. On the other hand, systems where gas giants have stayed in the outer regions, as they have in our own solar system, are considered more auspicious. The inner part of our solar system was not disrupted by migrating giants, which allowed Earth to form and maintain a stable orbit inside the habitable zone. This type of deductive reasoning helps astronomers prioritize which targets to investigate. With thousands of known exoplanet systems and a finite amount of available telescope time, choices must be made about where to focus attention. A clear understanding of the dynamics of various system architectures is what allows for those choices to be made with wisdom. The giant world we have explored tonight belongs to a crucial set of data that helps inform these very choices. Through the study of this planet and other hot Jupiters, we gain deeper insights into planetary migration, the architecture of distant solar systems, and the consequences of wandering giants. This accumulated knowledge is what steers the search toward more promising destinations in the cosmos. There is also a valuable contribution to the science of exoplanets from the amateur astronomy community, a role that often receives less recognition than it merits. While professional astronomers using major observatories are responsible for most initial exoplanet discoveries, amateur observers can and do provide essential support, especially through follow-up observations that help to confirm and characterize these new worlds. Observing planetary transits, in particular, is an area perfectly suited for amateur participation. Once a planet is found to transit its star, its recurring passages can be watched by anyone who has a telescope and camera with enough precision to register minor dips in brightness. Amateur astronomers located all around the globe have provided transit observations that have been instrumental in refining orbital parameters and searching for variations in timing. This kind of distributed network of observers offers distinct advantages. Professional observatories operate with limited time and face numerous competing demands for their resources. At any single location, unfavorable weather can obstruct observations during critical transit windows. But with a network of amateur observers spread out across the continents, the chances are very high that someone, somewhere, will have clear skies for any given celestial event. Several organized initiatives exist to coordinate these amateur contributions to exoplanet science. Such programs offer tools for collecting and analyzing data. They maintain comprehensive databases of observations, and they create a bridge between amateurs and professional astronomers who can utilize the information. For anyone with a telescope and a desire to contribute to scientific discovery, the study of transiting exoplanets presents a genuine opportunity. You can witness real transits, gather authentic data, and add to legitimate research. It remains one of the few fields where non-professionals can make truly meaningful contributions to the work of professional astronomy. The giant planet that has been our focus has been monitored by both amateur and professional observers. Its transit is relatively deep, at about 212%, making it detectable with modest equipment when viewing conditions are good. Observations from amateurs have been valuable in refining the transit's timing and confirming the consistency of the signal across many years. This unique collaboration between amateurs and professionals highlights something truly beautiful about the scientific process. The universe is a shared heritage, belonging to everyone. Any person with enough curiosity and patience can take part in the quest to understand it. The line separating the amateur from the professional is wonderfully permeable, with both sides united by a common passion for discovery. Still, significant mysteries persist about this planet and others of its kind. Despite many years of study, we lack a complete understanding of why some hot Jupiters are so much more inflated than others. It's an intriguing puzzle that planets with very similar masses and temperatures can exhibit vastly different radii. Some seem to puff up to enormous sizes, while others stay comparatively compact. What is the mechanism that determines which planets inflate and which do not? The answer likely involves, in part, the planet's history of formation and migration. Planets that migrated early in their system's life, when their stars were still young and highly active, may have undergone different heating processes than those that migrated later. The specific timing and the pathway of that migration could influence the final orbital arrangement, which in turn affects tidal heating. Variations in the interior composition, such as the size and makeup of a potential core, could also change how a planet reacts to external heat. But even these explanations do not tell the whole story. The observed spread in the relationship between radius and inflation is wider than our current models predict. Some fundamental element is clearly missing from our understanding. Another enduring mystery centers on the atmospheres of these planets. Observations have revealed that the atmospheres of hot Jupiters are surprisingly diverse. Some are shrouded in clouds or haze, their spectral features muted by these obscuring particles. Others, by contrast, are relatively clear, revealing strong signatures of water vapor and other molecules. What is it that dictates whether a specific planet will have a clear or a cloudy atmosphere? The formation of clouds is dependent on temperature, pressure, and composition in highly complex ways. The degree of vertical mixing within the atmosphere, that is, how efficiently material moves between different layers, influences where clouds can form and how dense they become. It's also possible that chemical reactions in the upper atmosphere can generate haze particles from simpler molecules. Even magnetic fields might shape atmospheric dynamics in ways that impact cloud coverage. To unravel these complex mysteries, we require both superior observations and more sophisticated models. The James Webb Space Telescope is now delivering observational data of unprecedented quality. At the same time, theorists are constructing increasingly detailed simulations. Progress is certainly being made, yet the big puzzles remain. Our record-holding planet, as one of the most extreme examples of inflation known, serves as an invaluable data point for this research. Whatever physical processes are responsible for causing inflation must be operating at their maximum strength on this world. By examining it in great detail, we may be able to isolate which of these mechanisms are the most significant. There are also broader philosophical implications to consider when we encounter worlds so profoundly different from anything in our own experience. Humanity has always looked to the stars and wondered about the nature of the cosmos and our place within it. Ancient civilizations wove elaborate myths to explain the heavens. Philosophers debated whether the universe was finite or infinite, whether other worlds existed, and whether those worlds might harbor life. For the vast majority of human history, these were questions without any possible answers. We could speculate endlessly about what might lie beyond Earth, but we possessed no means of knowing for sure. The universe was a vast, dark unknown, a canvas for our imagination but a void in terms of facts. The discovery of exoplanets has changed everything. We now know that other worlds exist, not as a matter of speculation, but as a measured reality. We can determine their sizes, their masses, their temperatures, and even the compositions of their atmospheres. We have begun to replace imagination with knowledge. And what this new knowledge has revealed is a universe far stranger than most imaginations ever conceived. We have found gas giants in searingly close orbits, planets so light they would float in water, and worlds where iron might rain from the clouds. The cosmos, it turns out, is not merely a repetition of the patterns we see close to home. It is endlessly creative, filled with possibilities we never thought to envision. This realization is transformative. It suggests that whatever else the universe holds, be it life, or intelligence, or phenomena we cannot yet imagine, we should not expect it to resemble what we already know. The universe has already surprised us time and again. It will undoubtedly surprise us in the future. This cultivated openness to surprise is perhaps the most vital attitude we can adopt. Science moves forward by following the evidence wherever it leads, especially when it guides us toward the unexpected. The most significant scientific advancements often emerge from data that conflicts with accepted theories. These are the anomalies, the outliers that necessitate entirely new ways of thinking. The worlds known as hot Jupiters represented just such an anomaly. They simply did not align with the prevailing model of planet formation, which held that gas giants must materialize far from the heat of their parent stars. Their discovery compelled a fundamental revision of that model, which in turn led to our modern understanding of planetary migration. In essence, the universe revealed a process we had not previously considered. It makes one wonder what else we might learn if we simply stay open to being surprised. What other core assumptions might the cosmos be waiting to overturn? We have no way of knowing ahead of time, and that uncertainty is part of what makes the scientific endeavor so compelling. The future remains truly unwritten, filled with discoveries yet to be made. The history of exoplanet research provides a useful perspective on where this journey might take us in the coming decades. It was in 1995 that the first exoplanet was confirmed to be orbiting a star similar to our Sun. Now, roughly 30 years later, that number has grown to over 5,700 confirmed worlds. The pace of these discoveries has quickened dramatically, from just a few each year in the early period to hundreds or even thousands annually, thanks to space observatories like Kepler and TESS. If this rate of progress is maintained, we could have catalogs containing 50,000 or perhaps 100,000 exoplanets by the middle of this century. Even more significant than the sheer numbers will be the depth of our knowledge about the planets we find. The characterization of atmospheres, a technique currently feasible for only a tiny percentage of known planets, will likely become a standard practice. By that time, it is conceivable we may have found indications of life on another world. Or, conversely, we may have established that life is exceptionally rare, at least within our corner of the galaxy. Either discovery would profoundly reshape our perception of ourselves and our place in the universe. The colossal planet we have been considering tonight will, by then, be seen as a historical footnote, one of the foundational discoveries that helped define the field. Future astronomers will likely view our current time as a pioneering age, the moment when humanity first began to grasp the true diversity of planetary systems. They will possess instruments and knowledge that we can scarcely conceive of today, just as we have technologies that would have seemed like magic to astronomers a century ago. This is the fundamental trajectory of science. Every generation builds upon the work of the past, adds its own contributions, and then passes that legacy to the next. The discoveries we are making today will become the foundation for breakthroughs we cannot yet imagine. The questions we manage to answer will give rise to new questions we have not yet learned to ask. This represents one of the most hopeful qualities of the scientific process. It is not a static body of knowledge, but a living, growing endeavor, constantly advancing and deepening its understanding. Whatever challenges we may face as a species, our comprehension of the cosmos continues to expand. That growing understanding is a profound gift to all future generations, even if we cannot predict precisely how they will use it. This seems a fitting moment for a quiet meditation on perspective and our own place within this grand cosmos. You are a conscious mind, living on a small, rocky planet that traces a path around an ordinary star, which itself is one of hundreds of billions of stars inside a single galaxy. And your galaxy is but one of trillions within the observable universe. The universe itself is nearly 14 billion years old and is expected to endure for trillions more. From a cosmic standpoint, your existence is remarkably brief, and your physical scale is infinitesimal. The giant planet discussed tonight is so vast it could hold 12,000 Earths. The distance to it is so immense that its light requires a millennium to cross the void. The universe extends far beyond that point, filled with wonders we will never directly witness. And yet, here you are, an arrangement of atoms that has developed the capacity to think, to wonder, and to pose questions about the very cosmos that gave rise to it. There is something remarkable in that, something precious. It is a quiet miracle woven into the ordinary fact of your existence. When you gaze into the night sky, you are not just seeing distant points of light. You are taking part in a great tradition of wonder that extends back to the very first humans who looked at the stars and asked what they could be. You are connected through time to every philosopher who contemplated the heavens, every astronomer who charted their movements, and every scientist who sought to understand their nature. This connection also extends across space. The atoms that make up your body were forged in the hearts of stars, much like the one this giant planet orbits. The hydrogen in the water you drink is the same primordial hydrogen that constitutes most of that faraway world. The iron in your blood was synthesized in supernova explosions billions of years ago and scattered through space, eventually becoming part of the planet you call home. You are an integral part of the universe, and the universe is an integral part of you. This is not a metaphor. It is a literal truth, written into the atomic structure of your being. The giant planet, orbiting its distant star, has no awareness of your existence. It will continue its silent orbit long after you are gone, entirely indifferent to human concerns. But you are aware of it. Tonight, you have learned something about that world, adding one small piece to your personal map of the cosmos. That knowledge forges a connection to that remote place, a connection that is meaningful, even if only to you. Science offers this kind of profound linkage. It connects us to realities far beyond our immediate senses, expanding the very boundaries of what we can know and contemplate. It lifts us out of our small, daily affairs and places us within the context of a vast, strange, and beautiful universe. That context might feel comforting or perhaps intimidating, depending on one's disposition. But it is our reality, and there is inherent value in truth. To understand where we are and what surrounds us is always better than to remain unaware, even when that understanding highlights our own smallness. And perhaps there is a unique comfort in knowing that we do not reside in a dead, empty universe. Planets are common, many are bizarre and inhospitable, but they are their real places in our cosmic neighborhood. The cosmos is filled with worlds, with possibilities, with countless things we have yet to discover. What else is out there? What other wonders are waiting? We can never know until we look. And looking, always looking outward, is something humans do exceptionally well. Before we conclude, it is worth exploring a few more details about the physics of gas giant planets. Worlds like Jupiter, Saturn, and this distant record holder are fundamentally different from rocky planets such as Earth. They are not simply larger versions of our world with a solid surface buried beneath a thick atmosphere. They are another category of existence entirely, worlds where the line between atmosphere and interior dissolves into ambiguity. Here on Earth, there is a distinct boundary between the air above and the ground below. You can stand on the surface and gaze up at the sky. The atmosphere has a clearly defined base where it meets solid rock or liquid water. This transition is crisp and unmistakable. Gas giants possess no such boundary. When you journey deep into the atmosphere of a gas giant, the surrounding pressure mounts in a slow, continuous progression. As this pressure builds, the gas itself becomes increasingly compressed and concentrated. Eventually, a threshold is crossed where the density becomes so great that the gas starts to behave much more like a liquid. Yet, there is no abrupt change, no distinct surface to mark this transition where falling would cease. The atmosphere simply blends seamlessly into the planet's interior. This reality is what makes the concept of a gas giant's radius a somewhat fluid definition. For planets such as Jupiter and Saturn, the astronomical community has adopted a standard, defining the radius at the altitude where the atmospheric pressure is 1 bar, a figure that approximates the pressure at sea level on Earth. It is important to remember, however, that this is a useful convention rather than a true physical boundary. One could just as easily choose a different pressure level to define the radius, which would result in a different measurement. The situation becomes even more nuanced for worlds like the record-holding hot Jupiter. The extreme heat from its parent star causes the outer atmosphere to swell dramatically, forming a vast, extended envelope that gradually thins out into the vacuum of space. The question of where the planet truly ends and space begins is therefore a matter of definition. These ambiguities in terminology do not weaken the underlying science. Astronomers take great care to be precise about their definitions, ensuring consistency when they draw comparisons between different planets. The fundamental measurements, such as the depth of a transit or the amplitude of a radial velocity signal, are well-defined and unambiguous. From these, derived values like radius and mass are computed using standardized methodologies, which allows for valid and meaningful comparisons. Still, this lack of a clear edge highlights a fundamental truth about gas giants. They are not solid bodies with sharply defined perimeters. Instead, they are sprawling structures, incredibly dense at their centers and progressively more rarefied at their fringes, with no clear demarcation between what is inside and what is outside. This makes them profoundly different from the rocky planet we inhabit. The internal composition of gas giants remains a field of intense scientific inquiry. In the case of Jupiter, we have acquired detailed information from the Juno spacecraft, which has been in orbit since 2016, charting the planet's gravitational field with remarkable precision. This gravitational data acts as a map, revealing how mass is distributed throughout the planet and allowing scientists to deduce its internal architecture. What Juno's measurements have shown is that Jupiter's interior is significantly more complex than was predicted by simpler models. It appears that Jupiter does not have a compact, well-defined core of heavy elements, enveloped by a uniform layer of hydrogen and helium. The data instead suggests a dilute core, where heavy elements are intermingled throughout a vast portion of the planet's total volume. The boundary between this core and the outer envelope is indistinct and fuzzy, not sharp. For exoplanets, we lack this kind of direct measurement. We are unable to send probes to orbit these distant worlds and map their gravitational fields up close. The only information we can gather comes from remote observations, which primarily give us the planet's total mass and its overall radius. For the record-breaking planet in question, its exceptionally low density points to a highly unusual internal structure. If the planet possessed a large, dense core, its average density would be considerably higher. This low density reading implies one of several possibilities. Either its core is very small, or the core material has dissolved and mixed throughout the planet's interior, or perhaps a core never managed to form at all. A central objective in planetary science is to understand why different planets develop such varied internal structures. The explanation most likely lies in the specific circumstances of a planet's formation. Key factors would include how much solid material was available to build a core, the speed at which the planet gathered its immense gaseous envelope, and what processes occurred later as the planet cooled and evolved over eons. For hot Jupiters, the intense radiation from the nearby star introduces another layer of complexity. The enormous amount of heat flowing into the planet from above can influence how heat from the deep interior flows outward. The thermal profile of the interior is directly linked to the energy balance at the very top of the atmosphere. Any comprehensive model must therefore account for this intricate coupling, which makes the physics more challenging to simulate. All of these factors make hot Jupiters incredibly valuable laboratories for studying planetary physics. They exist under extreme conditions that we simply cannot reproduce on Earth. By observing how these planets respond to such environments, we gain deeper insights into the physics of planetary materials, the mechanisms of energy flow through these massive objects, and the fundamental processes that ultimately shape their structure. In all of modern exoplanet science, computer simulations have assumed a central and ever-growing importance. Our comprehension of these distant worlds is now profoundly shaped by highly sophisticated computer models. These simulations replicate the physics of planetary atmospheres and interiors, meticulously tracking the flow of energy, the interactions of chemicals, and the evolution of structures over time. For atmospheric models, scientists typically divide the atmosphere into a series of layers and monitor the physical and chemical conditions within each one. They calculate how stellar radiation is absorbed and re-emitted. They compute the development of winds and how they transport heat and other materials across the planet. They also follow the intricate chemical reactions that create and break down various molecular species. These simulations can be adjusted for different planetary parameters, allowing researchers to explore how an atmosphere might change if they alter its temperature, composition, gravity, or other variables. By comparing the output of these simulations with actual observations, scientists can deduce which set of conditions provides the best match for the real planet. For interior models, the focus is on solving equations that describe how pressure and temperature vary with depth, how heat is moved by convection and radiation, and how the planet itself contracts and cools over its lifetime. Such models can trace a planet's entire evolution, from its hot, newly formed state to its present-day condition billions of years later. A significant but crucial challenge is to combine atmospheric and interior models. The atmosphere, after all, rests upon the interior, and the two systems are intimately connected. Heat from the planet's core travels up through the atmosphere before escaping into space. Simultaneously, external heat from the star penetrates down into the atmosphere and can potentially reach the interior. Achieving an accurate representation of this coupling is essential for understanding worlds like our record-holding gas giant. Today's advanced simulations are run on powerful supercomputers and incorporate physics of increasing realism. They can now model three-dimensional atmospheric dynamics, keep track of hundreds of chemical species, and resolve details across multiple scales. The outputs are often visualized as simulated images or spectra, which can then be placed in direct comparison with observational data. These simulations have been indispensable for interpreting the observations of hot Jupiters. When a spectral signature reveals the presence of a particular molecule, it is the simulations that help us understand the broader implications of that discovery for the planet's overall composition, its temperature profile, and its atmospheric dynamics. It is this constant, dynamic interplay between observation and simulation that continues to propel the field forward. When new observations present details that simulations cannot account for, it signals that our models are incomplete. These failed explanations tell us that some essential physics is missing, which must then be incorporated. In turn, the improved models offer new predictions, motivating the next wave of observation. With every turn of this cycle, our comprehension grows more profound. Why, in the grander context of our lives, do stories such as this one hold significance? We find ourselves in an era of overwhelming information. The news cycles accelerate relentlessly, and our attention is scattered across an endless array of platforms and subjects. It can feel difficult to concentrate on any single topic long enough to truly understand it. Yet, some subjects are worthy of that deep attention, and the universe is certainly one of them. The discovery that other worlds exist, that planets trace paths around distant stars, and that the cosmos holds a variety far beyond what we once imagined, stands as one of the great revelations of our age. It is a truth that deserves more than a momentary glance. When you dedicate 2 hours to learning about a single planet, you are engaging in something of immense value. You are deliberately stepping away from the ceaseless pace of daily life to connect with something larger than yourself. You are exercising your innate capacity for wonder, for focused attention, and for deep contemplation of things that truly matter. This planet, of course, will not resolve any of your immediate challenges. Knowing of its existence will not assist you with paying bills, navigating personal relationships, or advancing in your career. In the strictest practical sense, this knowledge offers no utility. But human beings do not live by practicality alone. We have a fundamental need for meaning, for beauty, for awe, and for a connection to things greater than we are. We need to feel that the universe is intelligible, or at least that we are part of a sincere effort to make sense of it. We need narratives that expand our perspectives and challenge our assumptions. The story of this giant planet, the most massive ever found, orbiting a star over 1,000 light-years away, is precisely such a narrative. It transports you beyond the familiar and the mundane, into a cosmos of breathtaking scale and diversity. It is a quiet reminder that the universe is bigger than human affairs, that wonders persist whether or not we take notice, and that reality is stranger and more beautiful than we typically remember. Carrying this awareness with you enriches your life. It provides a sense of perspective when daily troubles seem to loom large. It offers rich material for reflection during quiet moments. It connects you to the long and noble human tradition of wondering about the stars. For that, I thank you for spending this time with me. Thank you for caring about a distant world you will never set foot on. Thank you for being curious about the universe. That curiosity is a precious gift. It is the very source of all our knowledge, all our progress, and all our understanding. So long as we continue to ask questions, to look upward, and to wonder what else might be out there, we are taking part in something truly noble. The largest planet ever discovered is out there at this very moment, following its orbit, entirely indifferent to our existence, yet completely available to our understanding. That availability, that openness to our inquiry, is what makes the entire endeavor of science possible. The universe does not hide itself from us. It simply waits for us to look, and when we do look, we find marvels. Before you go, allow me one final reflection. The planet we have discussed tonight has been circling its star for billions of years. Long before Earth existed, long before our own solar system began to form, this giant was already there, tracing its scorching path, utterly alone in the dark. It will still be there long after our civilization has risen and fallen, and long after whatever comes next has had its turn on this world. This planet does not measure time in human terms. It is not concerned with centuries or millennia. It simply exists, obeying the laws of physics, indifferent and, by any human standard, eternal. There is something both humbling and deeply comforting in that thought. The universe does not depend on us. It was here before we arrived, and will be here long after we are gone. Our existence is a brief chapter in a much, much longer story, a story that does not require our presence to continue. And yet, during our fleeting chapter, we have managed to reach out across the light years and learn something of that faraway world. We have added it to our catalogue of knowledge. We have given it a name, measured its properties, and speculated about its nature. In some small way, we have made it a part of our story too. That is what conscious beings do. We observe, we learn, and we integrate what we discover into our understanding of the world. The universe may not need us, but we need it. We need to know where we are and what lies around us. The understanding that this giant planet, the largest we have ever found, is now part of human knowledge is a profound achievement. Whatever happens to us, whatever the future may hold, we will have known of it. That knowledge is an accomplishment, small in cosmic terms, but very real in human terms. I hope this journey has been meaningful for you. I hope you carry a piece of it with you into your days ahead. The stars will be there whenever you need them, waiting to remind you of the vastness, the strangeness, and the beauty of reality. Good night, sleep well, and may you never look at the stars in quite the same way again.